My name is Jessica Shi, and I'll be presenting our work on theoretically and practically efficient parallel nucleus decomposition. And this is joint work with Lakshman Doolitala from UMD and Julian Shun from MIT. So we'll be focusing on this classic question of how do we cluster a graph? And one fundamental idea is this question of how well connected are certain nodes or subsets of nodes in a graph. And in some sense, these nodes or subsets of nodes can form the basis of good clusters. So one classic algorithm for identifying important nodes is this k-core algorithm. So a k-core is an induced subgraph where every vertex has degree at least k. And in the algorithm, we repeatedly find and remove the vertex with the minimum degree, and this will reveal the successive cores of the graph. So for instance, this graph here, every vertex has degree at least 2, so the entire graph is contained within a 2-core. And if we remove this green vertex, which is the vertex of minimum degree, we see that we're left with these 2 disconnected subgraphs where every vertex has degree at least 3, and so these are 2 disconnected 3 cores of the graph. And in some sense, these 3 cores form nice clusters. So one problem with k-core is if we have, say, a social network graph where the edges represent follower relationships, and we want to discover these densely connected subgraphs which represent friend groups. However, we could have one person from each friend group following some celebrity node here. So now if we apply the k-core algorithm, we see that the entire graph is within a 3-core because every vertex has degree at least 3. But we actually don't get any further information from the k-core algorithm because in the algorithm, we would first remove each of these blue vertices and remove this green vertex last, and we see that there are no further cores. So one solution is to look at a generalization called S-clique peeling. So now instead of looking at the degree of each vertex, we're concerned about the number of S-cliques that each vertex participates in, and the peeling process involves repeatedly finding and deleting the vertex with the minimum S-clique degree. So now in this example, this green celebrity vertex actually participates in no triangles or 3 cliques, and each of these blue vertices participates in 3 triangles each. So in the peeling process, we would first remove the celebrity vertex, and now we're left with these disconnected 3 triangle cores where every vertex participates in at least 3 triangles. And one further generalization is this problem of RS nucleus decomposition. So now instead of looking at vertices as first-class citizens, we're looking at R-cliques as first-class citizens. And what we're concerned about is the S-clique degree of each R-clique, or the number of S-cliques that each R-clique participates in. And in the decomposition process, we now repeatedly find and delete R-cliques with the minimum S-clique degree. So in this example here, if we let R equals 2 and S equals 3, what we're concerned about is the number of triangles that each edge participates in. Now, each of these dark gray edges participates in exactly 2 triangles each, and this light gray edge participates in no triangles. So in the decomposition process, we would first remove this light gray edge, and that would reveal these 2, 2, 3 nuclei where each edge participates in exactly 2 triangles each. And I'll note that for the case of R equals 2 and S equals 3, this problem is also known as K-truss. Also, I'll note that the S-clique peeling process doesn't actually reveal these 2 disconnected cores because every vertex participates in exactly 3 triangles each. So the entire graph is within a 3 triangle core, and we don't get any further information from the triangle peeling process. So to further motivate this, these are some examples from the original work of Sarius, Sesajri, Pienaar, and Catalyric, who introduced the RS nucleus decomposition problem. And they constructed these hierarchy graphs showing the core hierarchies for this Facebook graph with 88,000 edges. And each of these nodes in this graph represents a subset of vertices where the shape denotes the size and the color denotes the density. So you can see that we have some hierarchy information from k-core and from triangle peeling. But if we generalize even further to the 3-4 nucleus decomposition, you see that we have a much more varied hierarchy with many more subgraphs of various densities. So the main results of our work is new shared memory parallel algorithms for nucleus decomposition with strong theoretical guarantees, and we'll also present a comprehensive evaluation showing that we outperform the state-of-the-art parallel algorithms by a couple orders of magnitude. And to motivate this even further, I'll show some examples on a 30-core GCP instance with 2-way hyperthreading and 240 gigs of main memory. So this is some commodity hardware. And also on these real-world graphs, Skitter with 11 million edges, LiveJournal with 34 million edges, and ORCID with 117 million edges. And notably, the prior best sequential work on 3,4 nucleus decomposition by Sarius, Sasadri, Pinar, and Keter-Lyric, they implemented their algorithms and they're able to perform 3,4 nucleus decomposition on the skitter graph in 8.5 minutes, on the LiveJournal graph in just over 3 hours, but they reach our timeout limit of 6 hours for the ORCID graph. So as you can see, this is a computationally difficult problem. And I'll note that there's also been prior work on parallel nucleus decomposition. So Sarius, Sasadri, and Pinar implemented various parallel nucleus decomposition algorithms, and they're able to achieve some relatively significant speedups, notably on this ORCID graph, where it previously timed out at over 6 hours, they're able to finish in 1.3 hours. However, for some graphs, they don't receive that much speedups, notably on this LiveJournal graph, where their speedup goes from 3.3 hours to 3.2 hours. And one of the main issues is that this prior work on parallel nucleus decomposition is not theoretically efficient. So we implement a parallel theoretically efficient algorithm, and we're able to bring these running times down to 50 seconds for skitter, 14 minutes for LiveJournal, and 21 minutes for ORCID. And additionally, we implemented practical optimizations on top of this, and we're able to bring these running times down even further to 24 seconds for skitter, 3.3 minutes for LiveJournal, and 13 minutes for ORCID. So this is the main thesis of our work, that if we implement theoretically efficient and algorithms with practical optimizations, we can achieve fast and scalable implementations. So now I'll go into some preliminaries before talking about our actual algorithms. So we use the work span model for all of our theoretical bounds. So on the right here is a parallel computation graph showing the dependencies between various tasks. And the work is the total number of operations or the total number of nodes in this parallel computation graph. And the span is the longest dependency path or the longest directed path in this graph. And we use the work span model because the running time is upper bounded by work over the number of processors by big O of the span. And importantly, we'll be developing work-efficient algorithms where the work matches the best sequential time complexity. We'll also be using graph orientations in our algorithm. So we use this idea of arboricity. The arboricity of a graph is the minimum number of spanning force needed to cover all of the edges of the graph. You can think of it as a measure of sparsity, and it's upper bounded by O of the square root of m, where m is the number of edges. And in real-life graphs, this value is normally bounded by about polylogarithmic of the number of vertices. In particular, we'll be looking at C orientations, or a directing of the graph such that every vertex's out degree is upper bounded by C, and we'll be looking at arboricity orientations, or O of alpha orientations. So in our prior work by myself, Lakshman, and Julian, we developed 2 theoretically efficient arboricity orientation algorithms that we'll be using in our nucleus decomposition algorithms. So now I'll talk about our actual parallel nucleus decomposition algorithm. So I'll show this on an example graph on the left here, where r equals 3 and s equals 4. So we're concerned about the number of fork cliques that every triangle participates in. So we begin by directing the graph using an arboricity orientation. And then, so this is an example of the directed graph. And then we count the number of fork cliques per triangle using this directed graph. And we'll construct a bucketing structure that maps the triangles to a bucket based off the number of fork cliques that's contained within. So this triangle CDG on the bottom is not contained within any fork cliques. All of the triples in this fork clique A, B, E, and F are contained in exactly one fork clique except for the triangle ABE. And all of the triples in A, B, C, D, E, which is a 5 clique, are contained in exactly 2 fork cliques each except the triangle ABE. And this triangle ABE is contained within 3 fork cliques. So now we perform the peeling process. So we begin by peeling the set of triangles in parallel with the minimum fork clique count. So to start out with, this is just a set of CDG. And then we update the fork clique counts of the remaining triangles. So there's nothing to update here because CDG participated in no fork cliques. And now we repeat this process. So in the next set, we peel all triples in the set ABEF except the triangle ABE. And now we update the fork clique counts of the remaining triangles. And importantly, the fork clique count of this triangle ABE is updated to 2 fork cliques. And now in the last step, we peel all remaining triangles since they all have the minimum fork clique count of 2. And now we have an empty graph, so we're done with this peeling process. So these are the theoretical bounds for directing the graph using an arboricity orientation and counting the number of fork cliques per triangle. And this is from prior work by myself, Lakshman, and Julian. So I'll talk now in more detail about these two subgoals. So first, we need a way to create and maintain this bucketing structure that maps triangles to a bucket based off of the number of fork cliques. And also we need a way to update the fork clique counts of the remaining triangles. So the first subgoal is we need a way to keep track of triangles with the minimum fork clique count. In theory, we'll use a batch parallel Fibonacci heap developed by myself and Julian in prior work. It can support K insertions and O of K amortized expected work and log n span with high probability, and this extract min operation and log n amortized expected work and log n span with high probability. In practice, though, this is not efficient, so we'll use Julienne, which was developed by Lakshman, Guy Blalock, and Julian, and it's an efficient parallel bucketing structure. And I'll note that we also need an efficient way to store these arc cliques. And in order to save space, we'll use a combination of an array and a hash table, where the array is indexed by the first vertex in each arc clique, and the hash table, the key contains the remaining vertices in the arc clique, and the value is the number of S cliques that it participates in. And we can refer to arc cliques by their index in the last level tables, assuming that we store the last level tables contiguously in memory, which is an additional optimization that we implement for better cache behavior. And in particular, we show that we can obtain some significant space savings using this method compared to a standard hash table. And our space savings increase for larger RNS, and notably, we have an up to 2.5x reduction in space usage on 4-5 nucleus decomposition. So I won't go into more detail about these theoretical bounds. You can read about that in our paper. So now I'll talk about the second subgoal, where we update the S clique counts of the remaining arc cliques. So we need a way to update the S clique counts after peeling these arc cliques. In theory and practice, we use a key lemma that improves upon the previous best theoretical bounds for sequential nucleus decomposition. And in practice, we also use some software optimizations. So essentially, the idea here is we modify our parallel S clique counting subroutine to efficiently obtain the updated S clique counts from deleted arc cliques. And we use this theorem by Eden, Ron, and Seshadri that bounds the minimum degree of each vertex and over all of the cliques in the graph. And I won't go into detail about this theorem here, but you can read more about this in our paper. So these are the overall theoretical bounds for our algorithm. And I'll note that we also implemented some practical optimizations where we receive up to a 5x speedup over an optimized parallel nucleus decomposition implementation. So now I'll talk very briefly about some of the experiments. We use a 30-core GCP instance with two-way hyperthreading and 240 gigs of main memory, and we use real-world Stanford network analysis platform graphs. So this shows a comparison of our parallel nucleus decomposition implementation to the prior parallel nucleus decomposition implementations by Sarius, Seshadri, and Pinar. In fact, they have 3 different algorithms. This shows the speed up of our parallel implementation over the fastest of their 3 algorithms. So overall, we see speed ups of up to 55x with a median of 9x over the fastest of the 3 previous best parallel implementations for R equals 3 and S equals 4. And we also see up to 40x self-relative speedups for R less than S less than or equal to 7. And notably, we have these significant speedups because PND, AND, and ANDN are either have large span or are not work efficient or are not space efficient and run out of memory. So in conclusion, I've shown that shared memory parallel clustering algorithms developed with strong theoretical guarantees and practical optimizations can lead to highly efficient and scalable implementations. There are many future directions for future work, including different settings like dynamic settings and different classes of graphs, such as bipartite graphs. And all of our code is perfectly available at this GitHub here. And thank you for listening to this talk.